Okay, let's define, we're continuing with AP Calculus BC, section 10.11, find Taylor polynomial approximations of a function. In this video, we're going to define an nth degree Taylor polynomial, show you how to find one, and use it to approximate values of a function. And then we'll look and compare the values of the function and see how this works. Okay. So the first thing we want to know, recall, what we're doing with the Taylor polynomial, we talked about in the last video, we are using a polynomial function to approximate values for a function that's more difficult to calculate values for. And to do that, we have to do that in a neighborhood close to a value that we know for the function. So we're going to call that place where we know the value of the function, the point that we know is on the function, we're going to call that x equals a. So we say we center this polynomial at a. And so we're going to define an nth degree Taylor polynomial as, we'll call it the function p sub n, and it's going to be equal to the sum as I equals 0 to n of the ith derivative evaluated at the center, we're going to call that a, times x minus a to the nth power all over n factorial. This is what the Taylor degree the first degree polynomial is going to be, or the Taylor polynomial is going to be. Now, when I said the 0th degree, when I is equal to 0, the 0th derivative of the polynomial is going to be the polynomial itself. Sorry, is going to be the polynomial itself. So f sub 0, or f, the 0th derivative of f at a, is going to actually be f of a itself. So this is going to end up being f of a, that's the y value of the point we know on the function centered at a, plus the first derivative of the function evaluated at a times x minus a over 1 factorial. By the way, 0 factorial is 1. We talked about that the other day. And then if we were doing a second derivative, it would be f double prime evaluated at a times x minus a squared over, this will be 2 factorial. And then we're going to do plus dot dot dot, and I'm going to go ahead and carry on down here, plus, and this is going to be finally the nth derivative of f evaluated at a times x minus a, that should be an I up here in my, so I'll fix that in a minute, x minus a to the nth power over n factorial. And up here, like I'm telling you, this should have been an I. Because x minus a to the 0 power is going to be 0, or it's going to be 1. So this becomes f of a plus f prime of a plus x. So let's look and see how that works with an example for a function y equals the square root of x. Now, there are some points that we know, so we're going to look at this and we're going to use this to estimate a Taylor polynomial. Let's just do a second degree Taylor polynomial first. So this is going to be the second degree Taylor polynomial to approximate. Let's do 1.05 for the function, or sorry, f of 1.05 for the function f of x equals the square root of x. So if we're going to do the second degree Taylor polynomial, we need to know we're going to need to know what, let's say, we got to have a center for this, don't we? The easiest place to center this, if we're going to use the approximation for 1.05, is going to be at f of 1, because we know f of 1, we'll center this at 1. So our a is going to equal 1. And we know if our function is square root of x, f of 1 is going to be square root of 1 or just 1. And then we're going to go ahead and do the derivative of f prime, or f prime, evaluate that at 1. Let's go ahead and do the derivative of square root of x. We know that this is equal to x to the 1/2, right? And so when we take the derivative of that, we do 1/2. I'm just going to go ahead and write this in polynomial form times x to the negative 1/2. And so if we evaluate that at 1, we're plugging 1, get the negative 1/2, it's just going to be 1. So we're going to have 1/2 is f prime of 1. And then since we're doing a second degree polynomial, we need to take and find f double prime and evaluate that at 1. So we can find f double prime of x is going to be negative 1/4 times x to the negative 3/2. We evaluate that at 1, we get negative 1/4. And so this tells me that our second degree polynomial, or p sub 2 of x, is going to be centered at 1. We're centering at 1. The a up here is 1 now. So it's going to be f of 1 plus f prime of 1 times x minus 1 over, oops, we don't need the over there, because it's 1 factorial, it's just 1, plus f double prime at 1 times x minus 1 squared over 2 factorial. That's going to give us a second degree Taylor polynomial. So we're going to evaluate that at 1.05. And we already know that f of 1 is 1. We know that f prime of 1 is 1/2. So this is going to be 1/2. And 1.05 minus 1 is going to be 0.05. And f double prime at 1 is negative 1/4. And then times, we're going to have 1.05 minus 1 is going to be 0.05 squared now, over 2 factorial is just 2. So this is going to give us an approximation of 1 and 1/2 of 0.05 is going to be 1 plus 0.0025. Is that right? No, 0.025. And then this is going to give us minus, this is going to be 0.05 squared is going to be 0.0025 divided by 2, which is going to be 0.00125. So now we're going to have, I'm going to bring this up here. This is going to be p, so 1.05. It's going to equal, let's go ahead and do 1.025 minus, and then this is going to be 0.00125. If we add those together, yes, if we add those together, we'll get 0.05. So if I subtract that, it's minus 0.00125. Let's say that's going to equal 5. This is going to be 7. This is going to be 3. This is going to be 2, 0. 1.02370. Now, if I do the square root of 1.05 on my calculator, the actual value is 1.024695 and then some zeros and stuff. So you can see, sorry for the bells, that gives you a pretty good approximation. If we went ahead and did the third degree Taylor polynomial, we would get an even better approximation. So for an nth degree Taylor polynomial, we use this. Now, if we look at this, what happens, because we've matched those n derivatives when we create this nth degree Taylor polynomial, that means that all those derivatives match. So if we take the derivative of the polynomial p sub n, let me go ahead and make another page here. If we have a Taylor polynomial if we have p sub n of x is a Taylor polynomial for some function f of x, say centered at a, then for the first n derivatives of f of x, so this is f of 1 or f prime of x, f double prime of x, f triple prime of x, the fourth derivative of x, etc., all the way up to the nth derivative of x. They are equal to their corresponding derivatives of the Taylor polynomial. So we built the Taylor polynomial by matching those n derivatives, and that's all respectively. So f prime is equal to p prime, p sub n prime. And f double prime is equal to p double prime of n prime, p double prime of n, or sub n. And the fourth derivative of f is equal to the fourth derivative of p, so on and so forth. So anytime you're given a Taylor polynomial approximation for, let's say, a 10th degree, you could actually use that to calculate the first 10 derivatives of the function that even if you didn't know the function, you could calculate its first 10 derivatives at the center of that approximation. And so that is how we calculate the Taylor polynomial. Let's do another example. Let's go ahead and do this x times e to the x that I had you look at. Let's calculate, let's see what we had to do on that. See what I had on the plan. That was find the third degree Taylor polynomial for y equals x times e to the x. So let's go back over here. Sorry. So we want to find, I'm going to let f of x equal x times e to the x. And let's see where the center was. I can't remember where the center was. Expanded about x equals 0. Okay. That means the same thing as centered at x equals 0. So we need to calculate first f of 0. And it's pretty obvious in this function that f of 0 is equal to 0. Then we need to calculate the first 3 derivatives. So we're looking for p sub 3, third degree Taylor polynomial. So we want to find the first 3 derivatives. Now look, we're going to have to use the product rule here. So f prime of x is going to equal x times the derivative of e to the x plus e to the x times the derivative of x, which is just 1. And then f double prime of x is going to be the derivative of this. This first part is the same exact thing we just did, so it's going to be, again, x times e to the x plus e to the x. Now we're going to take the derivative of e to the x also and get another e to the x. So this is going to be x times e to the x plus 2e to the x. Now we're going to take the derivative of this to get the third derivative, because we're doing the third degree Taylor polynomial. And this again is the same as what we did the first time, so it's going to be x times e to the x plus e to the x. Oops. And then take the derivative of 2e to the x, and we're going to get 2e to the x again. So this is x times e to the x plus 3e to the x. Now you might be able to see right now that if we did the nth derivative or the nth degree Taylor polynomial, we could continue on, and this would just end up giving us x times e to the x plus n times e to the x. That would be the nth degree, the nth derivative here. So now we're going to evaluate the third degree polynomial. So the third degree polynomial, p sub 3 of x, is going to equal f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 times x minus 0 squared over 2 factorial plus f triple prime of 0 times x minus 0 cubed over 3 factorial. So now we need to evaluate all of these at 0, which is not going to be too bad because f prime of 0 is just going to be 0 plus 1, or 1. F double prime of 0 is going to be 0 plus 2, or 2. And f triple prime of 0 is going to be 3. So when we find this P3, we already evaluated f of 0. That's 0. And what you'll notice also is the x minus 0 squared is just x. X minus 0 is just x. X minus 0 squared is just x squared. And x minus 0 cubed is just x cubed. Okay, so we're going to have 0 for f of 0. Then we're going to have 1 times x plus 2 times x squared over 2 factorial plus 3 times x cubed. Oops, I didn't need all the parentheses there. Over 3 factorial. And you might already see that simplifies to this polynomial is equal to x plus the 2 factorial is just 2 times 1. So this becomes x squared. And this becomes x cubed over 2 because 3 times over 3 times 2 times 1 is just 1 over 2 times 1. So this becomes plus x cubed over 2. So that's the third degree Taylor polynomial that we could use to approximate values of this centered at 0. If we wanted to use this to approximate this function at x equals 1, which we can tell f of 1, we already know the value of f of 1. F of 1 is equal to e. This Taylor this polynomial, this third degree polynomial, we would evaluate p sub 3 at 1. And we would get 1 plus 1 plus 1/2 would be 2.5. We know that e is approximately 2.718. Oh, and that's one thing we need to do. We never want to say that f of x is equal to the approximation. If we wanted to give it in the end, if we're using it to approximate, we would say f of 1 is approximately equal to 2.5, but 2.7182, because remember the Taylor polynomials are always approximations when we have a finite degree Taylor polynomial. So this is how we use it to estimate. So this one's off a little bit, but if we carried that out to the fourth derivative, fifth derivative, sixth derivative, it would continue to get closer and closer and closer to the actual approximation. The real value in this, though, is that we can use this third degree Taylor polynomial to approximate this value at something like f of 0.1. Since we don't have a clue what e to the 0.1 is, we can use this and say p sub 3 of 0.1. I'm going to go ahead and say this is approximately equal to f of 0.1. Approximately equal to, right? Is equal to 0.1. And 0.1 squared is 0.01. And then we're going to have 0.1 cubed would be 0.001 over 2, which would be, these two together would make 0.11. And then this would be 0.0005. And so this would be equal to 0.1105. And we can take our calculator and evaluate that. F of 0.1 is actually 0.1 times e raised to the 0.1. F of 1, or f of 0.1, according to the calculator here, is 0.11051709, 18. So you can see we got a pretty good approximation for values close to 0. And that's exactly what we expected it to do. And that's how we create an nth degree Taylor polynomial, or finite degree Taylor polynomial, use it to approximate values of a function.